Welcome to The Explainer. Today, we're going to unpack the secret blueprint behind every single solar panel out there. It's an essential tool that scientists and engineers use to understand and predict solar power, and it's called the Single Diode Model.
All right, so here's the game plan. First, we're going to tackle the big why, like why even bother with the model? Then we'll actually build this thing piece by piece. We'll see how all the parts affect the power output, check out how it's used in the real world, and finally, we'll get honest about its limits and what's next.
Okay, first things first. Why do we even need to model a solar cell? I mean, can't we just build one and test it? Well, think about it. The amount of sunlight, the temperature, these things are changing constantly. Trying to test for every possible condition would be a nightmare. It'd take forever and cost a fortune. So we need a smarter way, a reliable way to predict performance.
And that's where the model comes in. This is really the key takeaway. The model acts like a bridge. On one side, you've got all this mind-bendingly complex quantum physics happening inside the semiconductor, and on the other, you have a simple, manageable electrical circuit that engineers can actually understand and work with. It's a translator, really.
So how do we build this bridge? Well, the most popular and foundational way is called the Single Diode Model, or SDM for short. The best way to think about it is like a recipe. It's got a few key ingredients, and when you put them all together in the right way, they perfectly mimic how a real solar cell behaves. So let's start cooking. Let's build this thing from the ground up.
Okay, ingredient number one. This is the engine of the whole operation, the photocurrent. This represents the absolute, pure, ideal amount of current you'd get if the cell were perfect and just soaking up sunlight. But, and this is a big but, in the real world, not all of that perfect current ever makes it out.
And the first reason why is the diode. You can think of it as a gatekeeper, but it's a leaky one. It represents this fundamental, unavoidable loss mechanism where some of those precious charge carriers just find each other and poof, they recombine before we ever get a chance to collect them for useful work.
All right, so for the current that does manage to escape that first loss, it immediately runs into a massive traffic jam. This is what we call the series resistance. It's basically a bottleneck, right? It's the physical resistance from the silicon itself and from the metal fingers on top of the cell that collect the electricity. It's literally slowing everything down.
And if that wasn't enough, there's one more problem: leaks. You have to account for these tiny, unintended electrical shortcuts that let current just leak away. This is the shunt resistance. It's almost always caused by tiny, microscopic defects from the manufacturing process, creating these little pathways for current to bypass the main circuit entirely.
So let's recap. We have our engine, the photocurrent. Then we have a fundamental loss path, a traffic jam, and a leak. And these components give us the 5 core parameters of our model. I want you to think of them like knobs on a control panel. Each one represents a real physical thing happening inside the cell. And by turning them, we can perfectly describe its behavior.
Okay, so we've built our model. Now for the fun part. Let's actually start turning those knobs. We're going to see exactly how tweaking each of these 5 parameters has a dramatic impact on the cell's real-world power output. And the best way to see that is on something called an IV curve, its performance fingerprint.
And this chart, this is beautiful. It shows you that direct, one-to-one connection between the abstract numbers in our model and the gritty physical reality of the solar cell. You can literally trace a line from something like series resistance right back to the real-world metal contacts on the cell, or from shunt resistance to those tiny manufacturing defects. It's all connected.
Let's zoom in on one of these parameters, N, the diode ideality factor. This one is a super powerful diagnostic tool. Basically, if you get a value of 1, that's perfect. That's your A+ student. It means your cell is behaving almost ideally, with very few losses happening right in the most important part, the junction.
But if that N value starts creeping up towards 2, that's a huge red flag. It's the model basically screaming at you that something is wrong. It tells you there are probably defects deep inside the junction itself, and those defects are killing your performance. It's a direct numerical measure of the cell's quality.
This table is such a great cheat sheet for cause and effect. Look at series resistance, for example. That's our traffic jam. If RS goes up, you can see it absolutely crushes your fill factor, which is a key metric for how efficient the cell is. But what's really interesting is that it has basically no effect on the cell's maximum voltage. These kinds of insights are what make the model so powerful.
Okay, but here's where things get a little weird, a little philosophical even. Researchers discovered this fascinating problem.
It turns out there can be an infinity of different combinations of these 5 parameters that all produce the exact same, perfect IV curve. Think about that. It means the model is amazing at predicting what the cell will do, but it might not be telling you the one single true physical story of what's happening inside.
So keeping that little paradox in mind, let's zoom out. How do people actually use this model in the real world? Because believe me, it is absolutely indispensable.
Yeah, this is not some abstract thing that just lives in a lab. The single diode model is a workhorse that's used across the entire life cycle of a solar panel. We can really break its roll down into 3 critical stages.
First up, design and simulation. Before a single panel is ever manufactured, engineers use this model as a virtual sandbox. They can test out different designs, predict how a module will perform in the blistering heat of Arizona versus the cloudy skies of Germany, and optimize the entire layout of a solar farm. This is absolutely crucial for proving a project will be profitable and, actually getting the money to build it.
Then, once the solar farm is built and running, the model's job changes. Now, it's all about performance monitoring. For any given moment, with a certain amount of sunlight and a certain temperature, the model calculates exactly what a healthy panel should be producing. So if the real-time data from the field doesn't match that prediction, alarms go off. It immediately tells operators, hey, go check this string of panels. Maybe it's dirty, maybe it's degrading faster than expected, or maybe there's a fault.
Okay, so we've talked about how great the SDM is. It's a total workhorse. But let's be honest, it's not perfect. No model is. It's an approximation of a very complex reality, and it's really important to know where it starts to break down.
So where does it struggle? Well, mostly at the extremes. Think about very low light conditions, like on a really overcast day, or at super high temperatures. In those situations, its accuracy can start to dip. It also has a bit of a hard time capturing some of the more, let's say, exotic loss mechanisms that happen in the newest, most advanced, high-efficiency solar cells.
And that's exactly why other, more complicated models exist. You might hear about the 2-diode model, for example. It basically adds another diode to the circuit diagram to get a bit more accuracy, especially in those tricky low-light situations. But it also means more parameters and more computing power. It's the classic engineering trade-off, right? Do you need something that's fast and good enough? Or do you need something that's slower but more precise?
But at the end of the day, here's what you really need to remember. The single diode model is the foundational workhorse of the entire solar industry. It strikes this beautiful, elegant balance between being simple enough to use quickly and accurate enough to be incredibly reliable. It's the tool that makes modern solar power predictable. And that brings us back to that strange little puzzle we mentioned earlier, that infinity of parameters problem. It leaves us with a really provocative question to chew on. If you have a model that can perfectly predict reality, but it might not be physically true, which is more important to an engineer? A perfect prediction or the absolute truth? Something to think about. Thanks for watching.